So I prepared I was asked to do a very basic introduction. And so it will be very basic. So the first picture, I got this picture from the Climathics. This is a food web, in La Grande Carissère. Near the Neuchâtel Lake. And what we can see basic species and intermediate species and top predators, which are not very dangerous here for us. But usually when we see a food web, we have several layers called trophic levels, and there are many interactions, and it's very complicated. And the underlying graph, we will see some picture of this graph, has been shaped during millions of years, so it is not a trivial stuff, it's very complicated, and there is no clear explanation of the structure of these webs at present time. Okay? So I start with a very simple example to explain the Volterra system. Here I took this from a very nice paper in Bulletin of Mathematical Biology. This was from the UCLA department, how to teach ecology and mathematical biology to students in biology. So there is a whole book, article and a book on this, okay? And so we see here we have two populations of sharks and tuna, and so since it is to teach to basic students, it's very simple, but we can represent the abundances of sharks and tuna on the plane, and after we can describe the Volterra differential equation. So basically, usually we have
Excuse me, do you mind moving the mouse out of the screen, please?
Yes. The what?
The mouse.
La souris, ouais, elle est...
Je ne vois pas.
Elle est au milieu.
Elle est au milieu de l'écran, là, la souris.
Elle est au milieu de l'écran.
Ah, ok.
Sur le panneau.
I was looking for a mouse. That I have only sharks and tuna.
Unexpected species.
So usually we describe the change in the number of sharks. It is the first time what is important to check here is that we have S on each.
Sorry, can you talk louder?
Ah yes, okay.
The camera.
So we see the S in every term here, so that S will become in front of a sum, okay? And why it is proportional to S? Because each shark gives rise to a descendant with some rate, every shark, so it's proportional to S. Here a death rate, for the same reason. And here you have the mass action term. So you assume when you write such an equation that, for example, each shark can meet at randomly in a mean field case when there is no spatial structure, tuna, and so the mass action principle states that the probability to meet a tuna is proportional to the concentration of tuna, just because of this. And it is not symmetric because here, so it will be eaten, but this guy will transform. I speak under the control of the specialist, so I must be careful, but will transform the tuna in some sense in sharks. So this is a parameter to make this transformation. So usually we cannot solve this kind of equation because they are nonlinear, quadratic here. And so even if it looks like simple, even in 3 dimensions, you can have chaotic behaviors as soon as you have 3 species. Of course, once we have defined the differential equation, we have a vector field. So you know, to every point you have the two components here which define the vector. And so, in fact, defining a differential equation is equivalent to define a vector field, and solving in some sense, not numerically. The vector field is just looking for curves that are tangent to each vector at each location. Okay? And basic question, here we see a limit cycle, but you can have, will come here. So we have a vector field in general, two-dimensional here. And we see the vector field and the curve. So what is important in ecology, because I will speak of extinction, is equilibrium. So an equilibrium is a special state. So now we have a vector field which depends on x. X is x1, x2. And so we look for special x star such that the vector field vanishes. So this corresponds to constant solution. Okay? Because if I look at this differential equation, and if f of x is 0, the derivative is 0. Okay? And so the constant solution is solution of the differential equation. But what is so basically this, if there are some fixed points, some equilibria, then they will be very interesting in ecology. It's the first stuff that ecologists or ecologues look at. But we will say that such an equilibrium is feasible when it has every entry of x star is positive. Because if some entry is 0, then the component, which is 0, corresponds to extinction. So we will look for feasible solution. But such equilibria can be stable. That is, if I start near such an equilibrium, I will go to this equilibrium, and equilibria can be unstable. Okay, and there is a simple mathematical way, simple in some sense, is to look at the eigenvalue of the Jacobian matrix. So I will come to this point now. So first we look at stability. So we assume that we have an equilibrium, and we compute the Jacobian matrix, which is useful to make a local approximation of the vector field. And one can check that equilibrium is stable. That is, we are in this situation. The orbits are attracted locally by the constant solution when the eigenvalues of this matrix have a negative real parts. So what will happen in ecology and in climate change? So just to know, I am work in ecology since many years with Louis Felix, for example, but I am not an expert in climate change. And so I was asked to present something on this, and what will follow later is completely new. I didn't work myself. It's just to propose some ideas to develop a project, okay? So now we see a different way. We have two producers, X1 and X2. They might correspond to the basal species we saw in the first slide, and one consumer. So we have two layers, web, and we have competition between producers. The coefficient A is negative, because we can see in this equation. So now recall that the S was in front of the sums. So here it will be x1, x2, x2 in front of the expression. We have the production rate or birth rate. Theta will be negative. Theta is the intra-specific coefficient. Okay, so it will always be negative. A here is interspecific competition, is negative because they compete. And usually we put edges in this direction because S1 is eaten by S3, and the energy will be transmitted from x1 to x3. So usually ecologists write this graph in this way. Here we have the Lotka-Volterra differential equation. And we see the vector field. So now, as I told you, it's a basic introduction. Huh? I start with a very simple example. We have the vector field. And what we can see on this example, what we see here, climate change will change the parameters, the structure of the dynamical system. So if parameters change, it might change the nature, for example, of the equilibria. We can change from a stable situation to a not stable situation, and either to chaotic behavior. Okay? And this was the topic of my talk. So here, what we see, we have the consumer is X3. And so what we see is that if the competition is too high, so if the A is negative, if A is absolute value is larger than 1, then competition is too high and the consumer will become extinct. Okay, so this is a very simple example of how change in parameter can lead to change in the structure of the dynamical system. And so in the general case, we have the Lotka-Volterra differential equation. So the increase of xi is, again, proportional to xi. We have the birth rate, or the growth rate, if you want, the intraspecific competition. And here, we have the effect, the last term here, is the effect of all other species on species I. So S will denote the number of species. Aij is the per capita effect of species J on species I. Ri is the intrinsic growth rate. And theta, the intraspecific competition. This is a general Lotka-Volterra dynamic. It looks simple, but highly complex behavior. Very difficult to understand what is going on. So,
there's a question.
yes.
Why is theta not dependent on I? I mean, you assume that...
Yes, I assume. This is just to simplify.
Okay.
Yeah, just to simplify.
But is it a common assumption that the interspecific competition is like the same for every species?
No. Usually it depends on I. So it's a simplification, okay? We understand why we did this hypothesis later. It's a good question. Usually it depends on I. So we have our system, but now if we are in a predator-prey system, then if some Aij is positive, Aj is negative. Okay? If we have one predator, when we have pairwise interaction, it is like this. But we can have more general interaction. I just took the pairwise setting here, and this is what I said. The graph is directed, and when there is an arrow from A to J, this means that J consumes I. And we can have other kind of interaction, competition or mutualism, for example. For competition, both coefficients are negative. It was like in the toy model I just saw you before. And or mutualism, both can be positive. So we have signs. And here is an example. So we have a food web. And given this directed graph, we can associate the adjacency matrix. But in ecology, usually you see species as predator and species as prey. And just put one when a predator eats some prey. This is convention, okay? So this is a real example from the Bridge-Brook Lake matrix, experimental web. And what is very, very strange for me, we tried to understand this with fix during many years, is that if you take there are perhaps 12 or 20 empirical webs known.
No, there are more.
More now.
Oh, yes.
Okay.
That are described. It's very difficult to describe such a thing. Very, very
expensive.
difficult. So what is really difficult, it's easy to find what species are here, what is their role. It's extremely difficult to find out what is the interaction.
So sorry, I haven't understood the matrix. What is that, zeros and one that you're...
It's just to say some predator eats some prey. We better one.
So,
Yeah, but I don't understand what I see.
so
It's a one and the other are zero.
So the
Dot-
little point represents...
Dots are zero.
Okay, okay, thank
Yeah.
you. And
This
so,
is an empirical web, so from true data.
so, but each line is some species.
Yeah.
Okay.
But when you see such graph, you see here like predators and prey.
Okay.
You take a predator, it's not really, and it eats all this prey. And what is very strange, not strange, we can explain in some sense with some niche model, niche space, that when you do you can find always a permutation of the labeling, such that this matrix is lower triangle, almost lower triangular. It's not really lower triangular, but in most empirical webs, you can check, it is always the case. Okay, it's not very... So we can imagine that such webs were constructed during millions of years. So there is an underlying structure, but we do not understand this.
But how do you actually get those
So
matrices?
the specialist for this guy opens
so
the...
I did the first graph that you saw.
Yeah?
So it was a picture of the
The one with the owl and the other one, then...
So practically we went in the field during days. We sampled the species that were with different methods that were in our experimental sites. We had a list at the end of 400 species. And then come the interaction. I thought naively that I could go in the field and observe the interaction and during days and to try to have more and more observations of interactions. So at the end, you use to know who interacts with whom, and it's basically always done like that. You rely on the ecology of the species. And you know that this species eats a specialist or eating that and that. You see the list of your species, it can eat this one, and then you say that it's a potential link.
Okay.
There are few people who quantified this. There are some cases where
Quantify meaning other than zeros and
not only
one.
giving a one, but giving how much,
Okay. Okay.
or often.
All right. So if I understood correctly, so you go your vertices of the graph are from species that you actually observe with a team of people who put their boots and go in the field, okay? And so then you get your vertices, and then the edges you do it theoretically, looking up in the book. That's theoretically there's an edge here, and some people do it more precisely and say there is 50% of an edge. Okay, thanks.
Yes?
But how do you even have this knowledge and who specializes on...
Sorry?
Like, how do you even have this knowledge on what species eats what other species?
Wikipedia.
Here we go on books.
But, I mean, how do they know it in the books?
Sorry?
How do they know it in the books then? Because
They observe the species. You have many monographs on species. And if we don't have, if we have nothing, we know that the species, if we know the ecology of a species that is taxonomically close, we will use this information.
For example, with bacteria, it's impossible.
So it's guesswork.
So
Part of it is guesswork, right?
Sorry?
There's some guesswork involved.
There are some very good food web very well described because, for example, there is one on fish, and it's a colleague who capture thousands of fish and open them and check at what is inside. And with that, he could make a very nice quantified networks.
Okay.
But also, it's just in the river that is studied in different rivers. There are other species that all the diatoms, all the insects, what they eat, and so on. So it's a very complex.
So you're saying that, so such graphs have been, you're saying that there's like, this one has how many vertices?
I choose small one. I choose a small one.
So that you could
But
show
you
it.
have up to 100, 150.
Bridgebrook Lake, it's from a collection. This one, it's from a collection of about 50 lakes that were described in USA. 50 small lakes where they had the fishes and they had the information on the phytoplankton, the zooplankton, and so on, and the interaction were guessed. Where if in fact they can produce what sometimes they call a meta web, so they have all the species as all the species on all the species, and you put an interaction if you have a good evidence that a predator will eat a prey.
Okay, all right. Thank you.
Okay.
So in this graph, do I understand correctly that the top predator eats itself?
Yeah, of course, I can do it.
Especially in fishes.
It's very common. I thought it was rare, but not. Yes.
So you guess that this triangular
It's
method
related
is
to-
it's some code for resilience of the ecosystem?
Yes, we try to do this. We try to understand this. The effect of the structure on the dynamics.
Because on
It's
the
not realized, it's not known exactly.
because
Very difficult.
on mutualistic networks there's something called nestedness.
Yeah, it's a
And I-
specialist.
Absolutely.
So it's kind of the same thing but in the
No, I'm not the specialist. Rudolf is the specialist. But it's true that the nested structure tend to stabilize what they call mutualistic networks. And for the trophic networks like this one, it's destabilizing. What is stabilizing is more having groups. If you have groups, so here you could almost see two groups. You see, you have a higher density of between the species. That probably you could make 2 or 3 groups of prey, and same thing for the predators. So if you have the structure in groups, then it is stabilizing for predatory interaction. So we know that it has the structure has an influence indeed on the stability of the system. But again, it can be go in so many directions.
We might look at the effect on the values of the Jacobian or even on feasibility. Yes?
In some models, when you want to know the dynamics from a matrix, you take the powers of the exponential of the matrix. Is it the case for this model? Do you need to...
No.
So the fact it is lower triangular does not mean it is nilpotent or something like that, and you have no.
We tried, there are many papers on the role of the structure on the eigenvalues of the matrix, but it's very difficult.
Okay.
It's not known exactly. I know many references dealing with this, but it's difficult. Mathematical problem to understand this. But we will find something now because of these difficulties. People try to use random models, so they choose random webs, random adjacency matrices, and the first class of model A is the random graph, Erdős-Renyi random graph model, called the mean field model. It's just to check what happens when we can do some computation, when we can use mathematics, okay? But it is very important in ecology, this model. This was developed by Robert May. The second one here is a cascade model. They try to develop random webs that looks like true webs, with some hierarchy, some structure, and so on. This model is not so good for many reasons, and the niche model is based on the notion of ecological niche in a random way, and is quite good, okay? And there is also the nested hierarchy model from Louis Felix and co-authors. I didn't describe here, but we will see it again after. So basically for random webs, we choose edges at random with some probability. Here C is just a fraction of the total number of edges divided by the number of possible edges. And what is very, very difficult in this setting is that in most empirical networks, like we saw the lake before, nobody knows what is R, the growth rate. It's almost, when I was beginning to discuss with Felix, I thought it was trivial to know R. No, it's highly difficult to measure it. And of course, the interaction are completely unknown. Nobody knows in ecology what are the R and the IAIJ. So the only possibility to study what is the global effect of the structure and so on is to take this as random. We can just fix this value. That's why random matrix theory appears in this setting. You cannot avoid this. And they use such model to manage natural parks and so on. Even random matrix theory with random R and A to check if there is an equilibrium or not, if they introduce a new species, a new predator. I discussed with one guy in a natural parks specialist, and he was using this kind of model. So we will introduce also an interaction strength. So why? Because here we see three situations. We divide, so this is the algebraic version of the dynamical system, which just means the Hadamard product. You just multiply each entry by XA and the sum. And here we see the growth rate, the intra-specific competition, our interaction matrix, and we divide with the normalization, and we will choose 1/2 here, because if you assume that the coefficient are random, and you look at the variance of the interaction, it will remain bounded. There is no reason, because if you are in a species-rich systems, why this should affect too much interaction between species. So people may use this regime to make sure that it is well normalized. But we will consider moderate interaction, strong interaction when the coefficient is smaller than 1/2, and weak interaction when it is larger than 1/2. So now we look for given a random realization of the weights, perhaps with a given graph structure from an empirical full web, since we do know the interaction. Okay, we have a random matrix. This random matrix can be like matrix, like people in mathematics study. Most study in random matrix theory deals with random graphs. Okay, there is no structure, because random matrices having structures are completely unknown. Nobody knows how to study these random matrices at present time. There are exceptions, okay? But in most cases, we have no idea of the spectrum, what is the behavior of the eigenvalues, and so on. And so, what are the roles of topologies and interaction on feasibility, positive no extension, and stability? So what I said, there is no clear answer at present time. And now I will introduce a second class of model, which is of very strong use in many. It is just a Lotka-Volterra system with 2 layers.
So yes, I just have a little question before. When you do your random model, do you have nice observables you can compare to reality? Because you said that the interaction matrix, you don't have it, the growth rate, you don't have it, but you have certainly some stuff you can compare to what you get.
There are domains where you can measure effectively the number of species. Like we do, I'm studying with Xavier now and Isaline, random webs associated to bacteria. So we can measure with some techniques how many bacteria we have, colonies, and so on. Okay? And you are a domain that you cannot measure. It's impossible to measure the abundance. Difficult.
Well, it's difficult. Well, it's clear that you go from a network to the dynamic. It's not really. And when Christian said that we have no idea of the R or of the alpha, we can measure them in simple systems, but in a real system here we have no idea. It's impossible to measure. People very often use the body mass of the species to have meaningful estimates of the parameters, because it's known that R, the growth rate, tends to become smaller if you are a larger animal and so on. So you can use this what we call allometric relationship to have guess estimates of the parameters.
Sorry, they use the body mass also for the AIJ?
Yes.
Yes.
That's amazing. Yeah. You can make a statistical model like a logistic regression, where you put inside information about body weights as a explanatory variable. And if we did this with Climathics, and we can predict the webs quite well in some cases using body weights.
Using body weight, you can predict.
Some parts.
Oh, so you make your random model using body weights.
As a variable, as an exploratory.
Okay.
variable.
So, all right. So it means that the
Make a logistic relation.
randomness is dictated by the body mass. Is that what you're
By
saying?
the ratio of body mass between the prey and the predator.
Okay.
That's what quite well. In
Okay.
fact,
What does it mean to work quite well?
I can show a graph of. I can show after if you want.
Yeah.
We have a paper in Mac about that where we try. It was one of the first statistical model for. So you have the network of interaction that is observed, and you want to predict it, and we predicted it with the ratio of the body mass of the prey over the predator, I think, or the opposite. And then we have it's like a logistic regression. Well, but then we added that, but the first one had no latent thing. But it's like so basically, if the predator and the prey are in a range of ratios, there will we predict an interaction. Otherwise, there are two different. The predator is either too small or too large to eat that prey.
Okay.
And with that, we can predict quite well who will eat whom. So we need an observed food web. We need the body weight of the species that are here, and with that, we can make this model. Very simple model. And
Right, but then when you say that it predicts well, it means that you compare it with actual data and you measure the distance of what you get,
Yes.
or like, but you produce several random models, so you'll have several distances.
Here there's no
fitting.
Here there is no random model. In that case, there was only observed food webs.
Okay, and a deterministic way of.
We try to estimate.
There is a random model because we have a logistic regression.
Okay,
Okay,
that's clear.
but it's the spirit of statistics.
Mhm.
You have observation and then you try to estimate the parameters.
But if you don't have any ground truth, how can you compare?
Sorry?
it? Like how can you say it predicts well if you don't have a ground truth? If you don't.
We had the observer, like the matrix here.
It's only with
It's
observation.
like the previous matrix. This is our observation, it's a matrix.
Okay, I mean it's not a real ground truth, but it comes near to it, I guess.
In this case, it was really because it was observed. Yeah, it's,
Like with cutting open fish, you mean, or?
yeah.
Okay, I see.
So here is one of the most famous model, MacArthur model, 2 layers. Producer, we have seen a small example, there's 2 layers. Producer and consumer. So this is an equation for the consumer. So the resources are called RK. There is this coefficient plays the role of the IAJ before. We have here death rate. So we can interpret this, but it is more or less a Lotka Volterra, and we just say that the species, the consumers eat the producers. Okay? And you have an equation for the producers, it's like a Lotka Volterra. Here, a logistic term, this corresponds just to the previous model. There is always in most Lotka-Volterra models, the first term is a logistic model. Okay? And after you add in the data interaction. And here you have the fact that they are eaten from the consumers. And so MacArthur supposes a quasi-equilibrium, that is, he assumes that the basic producer equilibrates quite quickly as compared to the producer eating producers. And so you put the derivative to 0, and you get a linear equation, you solve it, and you plug this into the first equation, okay? And you get a Lotka-Volterra system only for the producers. And in this case, what is very, very important is that the matrix is symmetric. And so MacArthur used this fact to show that in this case, the dynamical system has a Lyapunov function. So there is a unique globally stable equilibrium. So the trajectory will converge all to a given point. But what is important here is because this matrix, if you write this in a matrix form, the matrix will be like a covariance matrix. It will have a low rank. And so if you study the equilibrium, you have a lot of extinction, even in this simple model. That is, you will not find in most cases a positive equilibrium. Okay? Basically, it states that the mathematical structure of the model makes that it is natural to have extinction. And so we'll present result on stability and feasibility, and Louis Felix will study in this part this model, where you have the MacArthur model, and you add direct interaction between consumers. And he will explain the role of climate change in this model. And they did experiment on this, okay? So we have experimental data. But if I start again from my equation, this is a general Lotka-Volterra, not the MacArthur, the general Lotka-Volterra. I put for simplicity C is 1 here. So this is really the random graph for May, okay? Well, you need to add random every edge with some probability. And we will choose A and R at random also, okay? But if you look for the equilibria, you have to solve this equation. And so if you look for the case with no extension, all the components of this guy are positive. So if you try to solve this equation, you have a linear system, okay, to solve. It looks simple. So R plus a matrix times the equilibria is 0. But the matrix A is random. So we have to solve a random linear system, and I will say something when the dimension becomes large. So basically, this is for equilibria. For stability, we have to look at the Jacobian matrix. If you do the computation, you can check that the Jacobian is a diagonal matrix having the xi star in the entries times this matrix. So I will follow May's approach, and May's approach is forgetting completely this. May's, when he did, it was a very famous paper of May, I will just explain, but he forgot completely this matrix and just focused on the eigenvalues of this matrix. So, but before May, in the 70s, MacArthur, the same of the model, was thinking, and most ecologists were thinking, that the more complex a web is, the more stable it is. Okay, this might seem intuitively clear or not. But
well, the argument was that it was really a verbal argument. And he said that if you have a complex network with, so if you have more paths through which the energy can flow, if you have one node that goes away, it's likely that you can continue to, the rest of the whole system will persist. So that was the major argument for that. And so he said that it was a very strong statement. He said that the number of species, so if you have more species, and the number of pathways, of interactions through which the energy can flow, is a direct measure of stability. He did not give how to measure that, but he said
it was like a good statement. Huh?
and all ecologists were, it was a kind of dogma in ecologists that if it's more complex, it will be more stable. And there were there is a list of 6 arguments in a book that says, yes, in the tropics it's more rich and we don't have evidence that we have communities that have strong oscillations. So that was one of the arguments. One of the arguments was to say, if we have a Lotka-Volterra equation with with one predator and one prey, it makes strong oscillations. That was what you see, very weak arguments. But it means nothing. Well, it assumes that if we would have, in fact, more species in the Lotka-Volterra system, it should have less oscillations. But in fact, it's exactly what May looked at. Mm-hmm. What do we have if we have the system of Lotka-Volterra equation, not only with 2 species, which has strong oscillation, but with more species? In fact,
so I have a question. So you have your n by n matrix with 0 and 1s. You actually have a number that you can get out of to get the measure of complexity?
No, they just the equation complex for it was the number of species.
Oh, it's just the n of the size.
Yeah, the number of edges between
okay,
them.
okay,
Yes,
but
exactly.
a diagonal n by n matrix could be...
The more stable it is, but it's wrong. They were convinced of it. And May came and used random matrix theory because when you have a random matrix with centered entries and some unit variance, for example, then it can be shown, this is called the circular law, that asymptotically the eigenvalues are located in a unit disk, complex disk. So this is quite a difficult, to prove this is not so easy. Eh? But this is one of the most standard random non-symmetric matrices. And so if you use this for your Jacobian, you get a condition. Here, May didn't have this coefficient. And so May, looking at this, observe that when S increases, at some point, this condition for ensuring that the eigenvalues have negative real parts will be crossed, okay? Will be saturated. And so he said that for species, he found that for species-rich systems, then they are always unstable. And so it was a complete contradiction with McCartney. And it was a big story when May found this. And so now I study with Louis Felix and some colleagues the probability of feasibility. That is, if you have this random matrix, then the X star is a solution of a random linear system, and the probability of feasibility is the probability that all species will persist, no extinction. And so we assume that the entry IID is centered, and we have here a moment condition. If, for example, I fix the R to 1, this means that the variance should be smaller than theta squared divided by 4. And we did some computation and found that asymptotically the entries of the solution of the random linear systems are IID, Gaussian, quite a technically difficult proof, but what we observed is that the probability of feasibility is decaying very fast to 0 as a function of S. This means that this is absolutely clear that most, according, if we adopt the Lotka-Volterra dynamics, most systems will exhibit mass extinction. Now, in how many years, okay? But it is very natural in system if we believe in the Lotka-Volterra to have mass extinction.
With random interactions.
With random interaction. But just within this modeling framework, okay? I don't know in reality, in nature, but if you could believe in what all ecologists believe in, the Lotka-Volterra, This is a consequence.
So if you start with 500 species, for example, wouldn't you have, for example, that 100 of them go extinct, but you still have a stable with
I will
400?
come to this point. This was the object of the work this afternoon.
Okay. Oh.
But so here it's the same. I can show that for mathematician an interesting phenomenon. Najim, Jamal Najim, is a specialist in France of random matrix theory. Yes.
I have another question on like the observations and the extinction. In a sense, when you observe an ecosystem in the food web, you observe those species that still exist after a long time. So in a way, you're conditioning on having a feasible equilibrium.
Yes, exactly.
Can one take that into account, saying like we sample our matrix in a way that we get a feasible equilibrium, or?
Well, but in what you presented here just before, it was purely random matrices. These were not observed matrices, of course.
Yeah. But like one could, in a way, try to condition the random matrix in such a way that there exists a feasible equilibrium.
This will appear, what we will see in if we take, we are, people are now on the way of estimating the fraction of the number of surviving species. It's already a difficult problem. Mm-hmm. And mathematically, to find an equation is rely on method of glassy system in theoretical physics, spin glass theory, because this problem with random is equivalent in difficulty to spin glass theory. So, and the only method to deal with this question is related to the cavity method of Parisi, Giorgio Parisi in physics, and it's very difficult. So we cannot. But people are trying to estimate now the number of surviving species and so on. Yes?
I mean, in a way, if you have a system of 500 species and a complete random interaction matrix, it's not really surprising that there might be at least one species that is not able to get enough energy from the food web to survive.
But that's a big fraction, a big proportion. It's not only one, it's...
But you were only showing the probability that every species
of course.
Right?
Yeah.
I think it's a good point that I didn't see who made it, but it was a good point to say that actually the food webs that we observe in reality already have seen a lot of extinction events, and then the argument that a food web that is existing and is complex might be more resilient to, for instance, one species like being removed is like still a valid argument in itself, right? I mean, you didn't really disprove the argument with it.
We just focus on the model and try to check what is the behavior of the linear equation solution. No, as a mathematician.
Perhaps a small remark is that it's true that there was this belief that complexity favors stability, and May in '72 came with a simple model that it was absolutely not the case. So if you increase the number of species and or if you increase the connectance or the proportion of interactions, then you are almost sure that the system will be non-stable. But he never considered the feasibility of the system. So this thing is valid for systems where you could have negative abundance at the equilibrium. So it's I would say a strong critique of the
May theory, yes.
And that's what is discussed here.
Yeah, so in a way he was just looking at a different situation.
Well, it has a huge impact on ecologists, this thing, because but it was really what was really good is that he said, well, in his book May said, well, we can say that at least the fact that diversity and connectance or complexity will increase the stability is not a mathematical, simple...
you have to give better arguments for it.
And then he said, well, we see that our communities are enduring with time, so now the task is to find the diffuse strategies that make real system persist. And it's here that ecologists started to look a bit better at what may be the structure that may have an effect, and we discussed that very rapidly with the idea of having a nested network of, or a network with, if we look only at the mutualistic part, and this is stabilizing. So again, the structure of the network may be stabilizing, and also the nature of the interactions. Here, in the work that we did here, we use what we call law of mass action that you explained to describe the interaction. If we use, and in the law of mass action, there is no saturation. See, if you imagine that you are a single predator and you have a lot of prey at disposal, then the amount of prey that should be eaten, it's alpha, or the factor that you have times this number. It's impossible. You have that sometimes in saturation. And if you use a function with a saturation, it's what we call in ecology the functional response. So we tried that with functional what we call Holling type 2 functional response. It's like a Michaelis-Menten, so it has a saturation. Everything, every situation is stable, whatever the structure. So you see that it's also.
But I mean, Holling type 2 is like a much better assumption than.
Of course, absolutely, absolutely.
So then, this doesn't tell us anything about it.
Then I would say that yes, it is that.
But for visibility, it does not change.
So I'm sorry, I think I still didn't really understand the feasibility, the definition.
So the probability that the solution of the random linear system is positive.
That we have no negative abundance at equilibrium.
Because you can prove easily that all solution remains positive. The Volterra equation.
Okay.
And so, if there is no equilibrium with strictly positive entries, then must reach the boundary of the space.
Okay.
So there must be extinction.
So the feasibility
is the probability.
Is the probability that nobody dies.
Exactly.
Okay.
Yes.
I want to ask if you cannot estimate the interaction metrics from the rate of change of the population from the past. Because I would imagine that the interaction doesn't change much with time, like certain animals like to eat certain other type of animals, but then you can observe how the population has changed in the past, right? So could you not estimate the metrics from the change in the past?
No, I did not fully understood your question, sorry, because I have a tinnitus, I have difficulties to hear you. So perhaps if you...
Well, we can discuss at the break and come to the break. So
if you don't mind.
You will speak after me.
Okay.
Okay?
Yes. So in this model we are basically taking 500 random animals together and then seeing how many survive after some time.
Yeah.
Okay.
Just to check what happens mathematically. But as Riffes told us, the discovery of may change completely ecology. Completely. And we see that it was perhaps wrong because they didn't focus on feasibility.
But again, he also assumed, well, he said nothing about the type of interaction, but we see that if we have interaction with saturation, and if we have weak interaction, it strongly stabilizes the system.
Of course, but it's...
And perhaps then structure may not be so much important than what we feel.
Just very briefly, what is the time frame for until an equilibrium is reached? I mean, I have not such a good intuition for these systems.
The time frame for
a system to reach an equilibrium?
Well, it really depends on the system. That's also a difficulties in these big things, because you may have producers that are bacteria and that have divide several times a day.
Sure.
Two things that are long-lived. So I think we, to my knowledge, there is only one network that is sampled with time since 30 years, where we have the interaction that change. But I think it would not be enough even to have data to test these models. So we would need much longer time frame. So I think having data for that, it's why it's the grist for theoretician, this thing, because we need that, and but unfortunately I think data for that. You could do something with you could do something with a system of bacteria, perhaps, and protists. That's what we use now, because in 1 week you have perhaps 60 generation of bacteria and 20 of protists.
But I don't know what protist is.
I don't know what, I will explain what is a protist.
Okay, so either I finish now in 3 minutes, because I will introduce the model that...
Well, you do have 3 minutes.
Yeah? 3 minutes. Okay. I will not speak of the phase transition. It's only for mathematicians. A difficult problem, but only interesting for math. And I will focus. So here we have the consumer Volterra system with a symmetric. As I told you, it is globally asymptotically stable because of the symmetry of the matrix. And I suggest to this afternoon, and what Louis Felix did also, to introduce a new model where we have a new matrix B here, a small immigration term, I. Here we have the matrix C times C transpose of the MacArthur model, and we had a random non-symmetric perturbation that might come directly from in your model. You have a model for the matrix gamma in your paper. So we add we have something symmetric and something exactly your model, this one, but I just wrote it in the stochastic way. Because here the attack rate you have in your paper is random, and here the interaction matrix is random. This is the mean. This, here it is the standard deviation, the variance of the attack rate. The way is the rate at which a consumer attack praise. It depends on temperature. We finish with consider a model where such quantities are depend on temperature, and yes, this is a model. So perturbation of the basic model with a non-symmetry. And what we see here you have enclosed the ground model without perturbation, the perturbed model. So we see that it can start from any system like MacArthur, which is globally asymptotic and stable. You add a small amount of non-symmetric interaction, then the spectrum will go to the here the eigenvalue should be positive, so instabilities. So in the ground model you have here species extinction, and you have always extinction. So a small portion is become extinct, the other converge to stable equilibria, positive. And if you add a small non-symmetric interaction, you have chaotic oscillation. And this might be very dangerous for the ecosystem. This is not rigorous mathematically. We are studying this now with Xavier and colleagues, perhaps with Felix. It's a new project. This is what I would like to study mathematically. And here you have a diagram where we will see this afternoon simulation. But you have a domain where you have the mean, the standard deviation, and you see a regime of fixed points. Here, a strong oscillation and unbounded growth, so the solution are diverging. And so we will see in more detail this afternoon. You will have a copy of the paper, and if you want to do simulation, you can see what happens with the various parameters. You see sigma C. But we see that there are kind of phase transition in the stability for system where I have a globally stable equilibrium and I had a small amount of non-symmetry, it changed completely the spectrum of the random matrix, and this leads to chaotic oscillation. That this might be the effect of climate change, I don't know, because in any case, without climate change, there are mass extinction. If we believe in the Lotka-Volterra model, and perhaps this might be the way climate change transforms the behavior of the dynamics. And Louis Felix will speak of this afternoon.
Your 3 minutes are gone.
Yeah, that's it.
Well, thank you very much.